So hello everyone, good afternoon. We will wait for a couple of more minutes so that others will all join. So then after we'll start our problem solving session of this Advanced Geomatics Engineering course. Hi, hello. So we'll wait for a couple of more minutes so that others can join. And then after we will start our session. Am I audible properly? Good evening. So we will wait till 3:05 and then we will start. I think we can start now. So hello everyone, good afternoon. Welcome to this problem solving session of Advanced Geomatics Engineering week 4. In this week, you might have learned some concepts related to remote sensing, what are the basic terminologies associated with remote sensing, and some fundamentals laws which are assigned with related with remote sensing. So before going to start, is there any particular doubt or anything? Okay, so what we'll do is this is like theoretical topic mostly. So I will just introduce some of the examples which is based on the application side, and then after we will start solving the question answer session in the last 40-50 minutes. So let's get started. So my name is Hiren Solanki. I'm a PhD scholar at Department of Art Sciences, IIT Gandhinagar, and I to work on the application of machine learning and deep learning in the field of hydrology and climate change. Apart from that, I work with the satellite data, geospatial engineering as well. So this doubt session we have every Saturday from 3 to 5 p.m. And if you log out in between, you can join the same session using this link, which is already being shared with you all. So before going to start, let's just look into like what do you see here. So as we are moving towards this chapter of remote sensing, it's all about analyzing images, which is taken from satellite, aircraft, drones, and other platforms. But the final output will get something like this. So what do you see here in this particular image? So any answers? What do you see here in this image? Yes. Yes. What else? So what kind of object you can find into this? Yes. So yes, exactly. And you can see, can you differentiate between different types of tree here? So from photo, yes, yes, canopy. You can use the canopy is large for those trees. Yes. So just highlight a few more things using my arrow. So you can see here that you can see some tall trees which are individual or separated. So maybe a coconut tree or some trees related to palm and all. And this place, if you see, it looks like some kind of beach view hotel or something because you can see the different geometries, so many parking areas also here. So it likes a commercial property where maybe a beach house or something else. And then you can see the patterns and the terrace of this particular buildings, which is having roof. Then obviously you can see the beach, kind of private beach. And then here you can see the coastal areas are like very shallow because you can see the surface also in which part it is deep or in which part it is shallow. So little bit idea about the depth you can also perceive from this image. And rest of the thing that you can also clearly see the here the different types of trees are there which are having very large density, and then some trees which are like artificially made or properly maintained, where you can see the proper grass land which is artificially maintained, and the trees around that also, and some trees around the roads. And roads also, when you talk about, so here you can see that this is the like roads with the concrete or cement on, or like with so like constructed roads. But here if you see in this part, they are the kacha roads where do not have any paved surface. So this kind of things you can identify the first glance when we look into this image, which comes to our mind is like the area is situated on some kind of beach or lake, probably a beach base. We can see the different coastal settings here. So that is the first thing which comes to our mind. Then we see the different homes, trees. So the idea is whenever you look into any image, how do you try to rectify or objectify, or you can identify different stuff out of it. So this is known as an image interpretation, which is very necessary skill when you start working with any remote sensing data or any image data. So when we do this kind of visual image interpretation, the first thing or first identification which we make, that is based on the tone or the texture, basically based on the color of the object. Then after the secondary identification which we do, that is depending on the size. So how big the house is, how small, then what is the shape of that house, whether it's a structured or it's aligned with like they are aligned with like making a colony or a very scattered growth or a proper growth with some kind of formations. And then texture will be useful like when you want to identify the different types of trees, whether bushes or the plant uh, plant surface or whether the properly maintained surface, that kind of things you can look into from texture. Apart from that, if rock and sands both are there, then you can also identify those two using their texture. As sand will have very loose texture, if you can see over here, whereas if you have another surface like where the soil is there, you can have very rough structure, as you can see in this image also with little bit of grass into it. And then roof, if you talk the size, shape, and also here you can see this area. The roofs are like having terrace on it. Whereas if you see here in this roofs, though they are like this slant roofs. So that kind of thing also you can identify from this interpretations. So after that, the third thing which we look for, and as we are going towards the higher things, it will increase the complexity of the image or how we perceive as the image. Then what we look into, what kind of pattern it is there, height, shadow. So when we talk about height and shadow, the image which we are referring, it is a 2D image. But as we learned earlier as well, that the concept of photogrammetry or the relief, we will get to know some perception about the height of the object or the shadow of the object. And as you can also see here that this coconut tree on the beach has some kind of shadow and we can perceive the height of it. Whereas if you see this trees which is on the road, that also you can perceive the shadow of those roads. And what else you can see the like if you see the different houses, then it will not have much shadow, it is not having much shadow of it. And we can say that it's a very like 1 or 2 story buildings only. And if you see some of the buildings, if it is big, then it will have a big shadow. Like if we see these buildings, then it might have 2 or 3 stories, so that its a shadow is more prominent here. Here also the big and continuous structure is making a very big shadow. And then here you can see the different things like playground is there on badminton or some kind of court is there. So this kind of thing. And then the second thing which you can see here, the after that pattern, we can see the proper growth is there or not, or whether the buildings are maintained by a particular party or it's just the individual houses, that you can also identify. Apart from that, on which location that particular site is situated and what are the association with the nearby object, that also you can detect, and this will also give you some idea for image interpretation. So these are the different tools, or you can say principles using which you can do the interpretations. And I mean this is required for any kind of images which you take in remote sensing. Now the another thing which you might have learned in this last week is about the resolution. So this is the kind of very basics in the remote sensing, which is a basic characteristics of the image which we are going to use. So there are four kinds of resolution, namely as a spatial resolution, temporal, radiometric, and spectral resolution. So spatial resolution, it means that the size or level of details which we can see in our image. Basically, it will define by the pixel size. So if our pixel size is very less, then it means we are having very high resolution image. So here you can see the 1 pixel. So here the task is there are some particular field and we want to detect those fields. So here what you can see is that if we have, let's say this black ones are the field which we want to recognize, and this red and yellow, and these are the pixel sizes which we have in our image, which is around approximately it is 208 meter. resolution. So here when we talk about resolution, it means the dimension of one pixel is 208 meters. So if you can take this to this. So this is 208 by 208 meter. And now if we try to resolve this farm, then we can't because it's just two or three farms and we are just getting one pixel only. And if we take all these six farms, then we are just getting four pixels through which we cannot resolve the shape of the farm. But now let's say we will increase this partial resolution by two times, or we can say will decrease the pixel size by half. So first of all, can anyone tell me that how many numbers of pixel will increase? How many times the number of pixels will increase? So what we are doing is we are having 208 meter and we are going to 104 meter. So what we are doing is we are making our pixel half. So we are doing something like this. So pixel size will increase by how many times? Can anyone tell me? Yeah, so the pixels will become four times. So now if we go to this image, then if we see this thing, it became four. But still, we are not able to resolve the fields which we have. So we will, let's say, again reduce the size of pixel by 50% or by half. So then this is the, see, this red and yellow ones are the boundaries which we have detected. Okay, so now we have reduced it by again 50%. So you can see now it started capturing the exact like shape of the particular farm, but still we are not exactly capturing or the detecting that particular field. So we will again reduce it by half. And now you can see here the red and yellow color in this particular figure. So now it is becoming more prominent that it is able to distinguish between red and yellow farms, and then it is taking the boundary also. But let's say again by we make it to 6.5 meter. So one pixel size will become 6.5 meter. Then it will become like it will exactly detect this particular farms. But if you see here, 13 meter is also fine for us. So now, let's say if you want to detect something, let's say you want to detect a house or you want to detect a building, then how much resolution is necessary to detect some particular object? So that question will come because based on that only we will select our data set. So if we are working with any application, let's say you want to do the land use land classification, it means in a given city, how many areas are water, how many areas are urban, how many areas are agriculture. You want to do sort kind of classification. And because of that, you have to identify different buildings. But now to identify buildings, we have to use some image which can resolve the building first of all, or if we want to resolve the water bodies, then we have to take some satellite data which in which we can see the proper water body. Otherwise it will not give us a proper idea, it will give the overestimation or underestimation of given feature. So for that the thumb rule which we follow is consider the minimum side of the object. Here in this case, if this is the farm which we are considering, let's say this is the farm which we are considering the red one. So the pixel resolution, like if you just want to detect this particular farm, then the pixel resolution should be half of the smaller dimension. So let's say if this smaller dimension is 10 meter, so your pixel resolution will be 5 meter or less than 5 meter. So that is a thumb rule which we follow in the remote sensing. And if you have the pixel size less than 5, then you can resolve that feature. It's not guaranteed that you can identify each and every edges exactly. So basically the minimum resolution which you need to resolve any object is the minimum length or width of any given object divided by 2, and below that. So that is a like if it is less than b by 2, then you can use those imageries only. So if we are considering about the building, so find out the smallest building in your area and take the smallest side of that particular building and divide it by 2. So pixel resolution should be less than that to identify that given object. Now, when we talk about the data, like we have to use images. So which image should we use? Like which way image will give you the 5-meter resolution data? Which image will give you me the 10-meter resolution data? So how do we decide that? So for that, there are a couple of satellites which are already in orbit, which gives us the data sets that we can check. So here we have this different satellites such as Modi's satellite, which gives the idea about the pixel size in Modi's is 250 by 250 meter. So the one pixel is 250 by 250 meter. And if you see, if you have this kind of pixels, you can visualize the global areas. So if you are interested in measuring something at global level, then you can go with the 250 by 250 meter resolution. But if you want to do some regional studies, such as if you are doing study on Gujarat, Maharashtra, or some any particular state or West India or something like that, then you can go with the this Landsat data, which is available like 30-meter pixel. Further, if you are doing with the district data, then you can go with the Sentinel satellite, which gives a uh, images at 10-meter resolution. And if you need a very high level street level maps, then you can go with this kind of quick bird imageries, which are very high resolution imagery and in which the pixel size is very less, and because of that the images are very high resolution. So before going further, can anyone have worked with any of the remote sensing data earlier? So which satellite data you have worked with? Okay, Lancet, basically the Lancet series. So you might have, so do you know that what is the pixel resolution which we have in Lancet? So this 30 meter same for all the band, or is it just for particular bands? Okay, so we will look into it. What does it offer? So it does not offer 30 meter for all the bands, but nowadays what data we are getting, it does some kind of processing and then after it giving us a 30 meter only. So for which band it is not giving 30-meter resolution, that we will check in this class only. So the another thing is a word is a temporal resolution. So this earlier one, which is a spatial resolution, which will define the size of your pixel or how much clarity will you have in your image or how much things you can resolve. Now this one will give us the how frequently you can resolve those things. So how many times you are getting the imagery. Suppose one image which we got on 1st of June 2006. Now the period after which we are getting the same image is around 17th of June. So we are having a gap of 16 days between two images. So if something will happen in between, then we will not able to collect the image. Here you can see the image of cyclone Mishang, which happened in 2023 in India. So you can see the part of like southern side where you can see the like there is two image. One image is captured on 17th of September, which is before the cyclone, how the images look like, and then one image just after the cyclone. So you can see the like what areas the cyclone affected. So you can see this entire area got flooded, and you can see this all the water bodies. Anyway, September is just a post monsoon season, so most of the water bodies already full. But you can see now because of this cyclone, it has created a lot of rainfall or the storms, and because of that, you can see the lot of other lakes are also became full. And this particular area, if you see, this became affected to flood. So this kind of information you can extract using the temporal data sets. So here this imagery is a I think Landsat imagery 30-meter resolution. So you can see if you want to do this kind of applications, you can use the Landsat imagery where we are looking for a regional specific data. So this is the basically the temporal resolution is how frequently you get the image, how after how many days you get the image. So in general, whatever the free satellites are available, this Landsat gives the data at every 16 days. There is another satellite called as Sentinel-1, Sentinel-2. They gives the data at weekly or 8-day scale. Then we have a Modi's satellite which gives the data at 250 meters spatial resolution and temporal resolution at 1 day or 1 week, depending on what kind of product you are using. So if you see the relationship between this temporal resolution and spatial resolution, they are both very opposite. Why? Because if you need a very high resolution of data, you cannot cover the entire Earth in just 1 day. You need a lots of revisit. So your satellite has to move a lot of time if you need very high resolution data. Why? Because your satellite will be near to the Earth in that case, and it will take time to go around, like to take a rounds around the Earth. And because of that, we will get the imagery at around 16 days or after that. Whereas if you need a very coarser resolution data or you are working with a world level studies, then you don't have to worry more about the temporal resolution because you can cover a image in just 1 day as well, because the resolution with which you are working is not that great. So it's a trade-off between temporal resolution and spatial resolution, which you have to make. If you are using the flooding application, if some flood happened in the city, then you have to go for a very high spatial resolution. Otherwise, it will not happen that you will detect the water into the given city. Similarly, if flood, landslide or something will happen, you have to go for high spatial plus high temporal resolution. Because let's say we take the example of the recent landslide which happened in the Dharali, Uttarkashi. So what happened there is the image which we got at 10-meter resolution is captured at the 1st of August, and the event happened around 5 or 6th August. So the next image is coming after 11th day. So the next image, like last image which we got on 1st August, and then we will get direct image on 11th of August. So and this particular landslide happened around 5 to 6 August. So it's just useless because after 2 or 3 days of the disaster, everything will settle down. We can still monitor something, but not exactly the what was the damage it caused and how much casualties it caused, that we cannot check using this thing. And because of that, lots of commercial companies are coming into the space of the satellite data acquisitions, which are also providing a solution to capture the very high resolution images at every day. So they are giving the image at every day with very high spatial resolution of like 4 meter or 1 meter. So there's a company name as a Planet Lab which provides this kind of image, and you might have heard of that. People have Maxcar is also there. So people have started before this attack happened between in India in the Pahalgam. So during that time also the people have purchased this high resolution imagery of that particular area, which gives the very high resolution and how frequently that place is changing. But that the temporal component is not that component. The more component, major component was the locations which is there in the satellite image. So high spatial resolution. So now you have to make a trade-off for whatever kind of application you are working with. According to that, you have to select your satellite data. So the next resolution, which is a radiometric resolution. So radiometric resolution is like how much details you can see in your image. Details in means not the size of the object, it means the what is the sensitivity of the object. If two green leaves are there, if I am able to differentiate between the shades of green or not. So that is like being shown by the radiometric resolution. So if radiometric resolution will be represented in terms of beat, the spatial resolution in terms of meter or any linear unit of measurement, temporal will be in the number of days, and then this radiometric resolution will be displayed as a beat. So if we have just one bit of imagery, then we can say it as a 2 raised to 1. So basically, if we have one bit of file or radiometric resolution, then it can store a data up to 2 to the power 1. So here if we say 2 to the power 1, so what we will get is 2. So if the image is just 1 bit, and it can store the 2 value only, which will be your white color and black color. Now if you take 2 bits, then it will become 2 to the power 2. So it can store now 4 different values in case of 2 bit. And 4 bit means the highest value will be white, lowest will be black, and the other two is the shades between black and white. Similarly, you have 7 bit of data, then you can represent it. So basically whatever the bit you have, you can represent your data like 0 to 0 to 2 to the power n minus 1. So that is the range which you can represent using the radiometric resolution. So higher the radiometric resolution, the more specific details or more specific tonal change you can see how much the colors are varying. Here in this image, if you see in the image in the right hand side, you can see here the area is just black only because the values are less than some threshold. But if you see in this image, then you can see there is a like very high density of trees in this particular location here and here, whereas in this image all of the place it looks same only, so there is no specific differentiation. And here if we use for same image, if we use 4 bit of data, then we can show the more amount of details as well. So that is a radiometric resolution. Now the last one is the spectral resolution. Spectral resolution, it means like when we talk about remote sensing data, we have electromagnetic spectrum associated with it. So what kind of energy which we are getting back from the satellite, that is being reflected in spectral resolution. So generally as a human eye, we can see this three lights only, R, G and B. If you take any phone cameras also, it will show you the this kind of things as well. So any image if you take, it will have just three bands, which is known as a RGB from your camera. But few things we can't see in this spectrum, or human eyes cannot see what is beyond this RGB spectrum. And because of that, we need to perceive other bands also, such as near infrared, ultraviolet, then radar band, and so forth and so forth. So for that, what we do is we put the sensors in our satellites, which can detect those bands which are coming from infrared, which are coming from microwave, and which are coming from radio waves. And then after we represent those bands as a RGB values, and that's why it will create an image, but with some different colors. So now, if we want to combine all those things, all the four resolution, and let's say if you are working with different applications, so how will you use those resolution? So first of thing, let's say we are working with forest cover mapping. So we want to map the areas which are there in our country. So for that, what we can do, like which spatial resolution we can use and which temporal resolution we can use. So as here written that we need very high spatial resolution, but the forest when we are considering it's very big. So it's not that we need very high resolution. 10 meter to 30 meter resolution will also work, until 100 meter is fine. And generally this you see Forest Survey of India, they publish their forest cover mapping every like once in a every 2 year. So if we get any good image between this also, like within the 2 year also, then also it is a fine. Similarly, if we have forest fire, now forest fire will happen in the very regional area. So we need very high resolution. And if it is a big fire, then we can go with till 500 meter of data also. And here, if we talk about the temporal resolution, it is very high. Why? Because this forest fire will become very quickly, and because of that all the place where it happened it will become black. And if we do not take image just after it, then what will happen, this will land will also become sometimes fertile because of the ashes and some other stuff. and because of that it will start going green again. So we'll forget some patches if some rain happened after the forest fire, or people have used water to reduce that fire. Because of that water availabilities, plants will nearby plants will also start getting greens, and we will lose the signature in the area where the forest fire occurred. Similarly, when we want to measure the temperature and rainfall or wind speed and so on and so forth, climate variables, then the spatial resolution which we need is around like 5 kilometer is also fine. 1 to 5 or 10 kilometer is fine for both the variable, and that thing you have seen very easily that it is raining in your area, but if you see in some area above or just above your home, or some areas below your home, that the rainfall is not happening at those locations. So rainfall is varying spatially very differently, very frequently, and because of that we need to get the this data sets at a very high resolution and at a very less time, because if you take the entire day's data, it will not make any sense that this particular rainfall came during which time. It's during afternoon, during morning, or some other time of the day or night. So that for that reason, we need very high resolution temporal plus spatial data sets. Then we have this other application of land use land cover. What we do in this application is we classify the different types of buildings, parks, water bodies, barren land, water areas, and so forth. So depending on the types of detail, if we did very detailed survey, then we do those surveys at very less time, like once in a 5 year or once in a 10 year, but with a high resolution. So similarly, like basically what kind of details we need in our data, we will select the satellite. If we need very high resolution detail, so we will use the high resolution data. If we need high resolution, but like once in a 2 year or once in a 3 year, then we can also go for the satellite data, which provides the data at a very high resolution as well, in compromising with the temporal resolution. Then we have DEM. So DEM is a 0 to 1 meter to 5 to 10 meters, which is like the elevation accuracy, and horizontal accuracy is as far as temporal accuracies of like this other products. So here are the different applications for which how much temporal resolution and how much spatial resolution is necessary. Any doubt in this part of resolutions and their application, how to use them? Any doubt? Okay, so now I think what we will do is we will see some of the actual data set so that you will get more idea about the type of resolution which we have in the original data with which we do work. So if you want to do the same thing in your system also, what you can do is you can write GEE, which is the Google Earth Engine data catalog. So you write GEE data catalog, which means Google Earth Engine data catalog. And then you can go to this Earth Engine data catalog. So here you can see a bunch of data sets which are already available free of cost in the Google Earth Engine. And you can see how they have organized the data: surface temperature, climate, atmospheric data, weather, imagery of Landsat, Sentinel, Moody's, and very high resolution imagery, and some other geophysical data such as the your like cloud cover, glacier cover, high resolution imagery, land cover, then terrain, agriculture, and other geophysical data such as like that. So let's get started, like see what kind of data we have in this portal. So we have this kind of data sets. So some ortho photos are also there. So you can go to the any. So this data set which I clicked just now, it is only available for Germany and this data set availability. So that data is available from 23rd August of 2021 to 20th January 2023. Uh, who is providing this data and how to call this data into the Google Earth Engine environment. And it has size of just zero point 0.2 meter. You can see that how much details we are going to have in this image. So that is a pixel size. It means it's which kind of resolution? Spatial resolution. Then we have bands here, as you can see, near infrared, red, green, and blue. So four bands we have. So this is which kind of resolution? Yes, it's a spectral resolution. So number of bands. Then what is the value of minimum value and maximum value in the band? And then this description about the particular given band. So it is a near infrared, red, green, or blue. So basically, if you want to, you can go to this. If you have account in Google Earth Engine, you can go and run this sample code also, so you can get to know that how this data will look like. So you can see now this. You can see this shadow of this particular building, which we learned in during the relief class and the height approximation class. So you can see this thing very well. You can zoom it also. So you can do this thing. After that, let's say some of the popular data sets which we have, such as Landsat, Sentinel, and all. So let's go and learn more about the Landsat data. High resolution imagery for Indian cities. I think it's not available, but 1 meter resolution is available. That is available at every month. So that is available on this Copernicus Earth observation platform, which you can know like just type the Sentinel Hub EO browser. So this platform they are having some fees, but this is available like for 15-day initial uses. So you can download your imageries, like you can directly download the GeoTIFF imagery in the geo-referenced format only for the given area, which is at very high resolution. So from this you can do that. And apart from that, what available is in free of cost for Indians, that is available at 10-meter resolution at max. So I think in Google Earth Engine also some data sets are there. Let me check. So if you write this planet public ortho imagery multispectral, so I think it's for entire world. So this is the free imagery which is available with how much resolution do we have? So I think it's a 2 meter resolution, this Planet Lab imageries. And this is generally collected between 2014 and 2016. So, so I will just request all of you that if you do not have this Google Earth Engine account, then please make it. If you have any issues, you can drop me email. Also, I will help you in setting up this thing. So this is a very good tool if you are working with remote sensing data, at least for visualization purpose and for some of the applications as well. And I can show some applications also in this if you have accounts. So you can do along with me as well. So this is now the 2 meter resolution, and let's say we'll start for like search for India region. So let me check if do we have or not. Yes. Yes, so that's a good point which you have raised. So generally, this Google Earth Engine codes are in JavaScript, and AI generally doesn't work well in the scripts. As of now, there some of like basic applications it will work, but if it will become complex, then you will not have good like script which will directly run without error. You will get a lot of error. So basically, to do a some basic course or medium moderate level course, then it will help you a lot in debugging your errors. And like no need to learn coding. So what you can do is you can just take a code and just try to understand that code and just change the variables, change the dates. So like that you can start. If you are interested, you can drop me an email. I will share you some of the course material of my codes which you can refer. Mm, so I think this is available for some of the places only, not for entire world. But yeah, if you want at monthly resolution in this, the images are there at 1 meter or 2 meter resolution. But this is available for 15 days only. After that, you have to pay or you have to create another account or something like that. So free access is still for 15 days, and then after you have to pay for it. So if you have this account, you can look into the Sentinel Hub EO browser, Earth observation browser. Yeah. Coming back to the our data sets, so let's now look into more about the other two data sets, which is a Sentinel and Landsat. So Landsat over here only it's written. So if you click on Landsat, we have this Landsat data sets. So there is a different Landsat 9, Landsat 8, 7, 6, 5, 4, 6 is not there, it's 5, 4, and then 1 to 5 data is there. So if you see this, these are the OLI or TIRS, these are the sensors which it has used while capturing the images. So this is the operational like thermal infrared sensors or some operational land sensors. So you can search more about so basically, some of them are imagers and some of them are sounders. Now, if you click on any of the one of the thing, Landsat 9 or Landsat 8, you will get the three different product. The first product is surface reflectance. Another product is top of the atmosphere reflectance, and third one is a raw image. So the difference between these three is uh, there's let's say raw image which is there. This is what you captured from the satellite. Now, top of the atmosphere, I think I will show you and then show, then you will get a better idea of it. So basically, we discussed that there are three different products. So the first product is raw images. That is just an image which you are getting directly from the like just directly from the satellite. Then after you have another thing which is known as the top of the atmosphere reflectance. So let's say this is your surface which you want to monitor using the satellite data, and you are having your satellites here somewhere, and these are the different clouds, and this is the sun from which your energy is coming. Okay, so first energy will go to the surface, and before going to surface also it will interact with the atmosphere as well, and then after it is going to the satellite. Now, if there is no cloud or nothing is there, whatever energy is here, it will directly reach there. I mean, so Just give me a second. Just give me a second. Sorry for the disturbance. So, okay. Okay, so when we take this imageries, so in terms of top of the atmospheric reflectance, what will happen that otherwise this uh, like energy will directly go to the satellite, but in terms of top of the atmosphere, like if clouds are here, then they will also emit some energy. Or what will happen, some energy which is coming from sun, it will directly go to this satellite. So top of the atmosphere, it is the combination of both. And when we talk about the surface reflectance, it means we are considering the energy which is coming from the surface only. So top of the atmosphere, it means it will consider the clouds or any other particle which are present in the atmosphere, as well as the reflectance from the objects. Whereas in the surface reflectance, it will just have a reflectance from the surface only. So now let's see that kind of imagery. So what do we have? So this is a surface reflectance. It means the whatever the effect which we have because of the atmosphere, that is being removed here, and here top of the atmosphere, it is like whatever we are getting, it is including the atmosphere. So let's say if I will click on the surface reflectance product. So you can see now this having pixel size of 30 meter. This imagery is started giving you the data like this particular satellite from 31st October 2021 till now, and revisit interval is 16 days. It means the temporal resolution of this satellite is 16 days. Spatial resolution is 30 meter. When we talk about the spectral resolution, then you can see that how many number of bands it has. It has band 1, which is ultraviolet, sorry, ultra blue or coastal aerosol. Then you have blue, green, red, near infrared, shortwave infrared 1, 2, and then some band for uh, temperature measurement. So that means that it uses the higher wavelength, and you can see the which wavelength it uses. That is also given here. Yeah. Do you have any questions, Shubham? Yeah, you can go ahead. Yes. So basically, it does not have much of the value. That's why we do not use. And staking when we do, so it depends on for which application you want to use. So you just want to do the just visualization. Then at a time you are just using three data sets only, like three bands only, not more than three. Because human eyes can see the colors in three window only, RGB. So it makes three band which we can visualize at a time, that is RGB or any other combination of bands. But number of bands is three only, not more than three. But when we do like this merging, when the like how it will be helpful if we are doing some applications such as land use line cover classification where we are training our models. In that case, we need more number of bands. So I will touch upon that topic just after a few minutes. That why we do not use this ultraviolet band or blue band or green band, or how it will helpful in the like object detection. I will go into that in this lecture only. Just give me a few minutes. After going through this, we are to that topic only. So apart from that, these are the other things which is already also available, which will give us the idea about the quality of the image. These are the unnecessary things, but it will give you about the how good your pixel is. So basically the quality standards. So we get to know the what is a temporal resolution, what is a spatial resolution, what is a spectral resolution, and can anyone see here the radiometric resolutions as well? So which particular parameter can you see it as a radiometric resolution? So if you see the bands, then first column is name, second one is the unit, then there is a value minimum and maximum. So that is a how many value that pixel can take. So if a given pixel, how much value it can take. So that what we discussed during the radiometric resolution. So how sensitive your pixel is through the different brightness levels. So here it is, there we are starting with 0, 0 to 1 or 0 to 8, 4 or 0 to 8 like that. And here we are talking about from 1 to 65,455. It means you can see, you can put just 2 raised to the n, what will you put, then you will get the 65,455. So around it will come 16 to 18 bit spatial resolution, if I'm not wrong. So that is the resolution which we use in this Landsat dataset. And if you want to know more about the other properties, you can always check the description of the file and you will find all the details about the datasets. Then the property, like if you download these data sets, what kind of property you will get. So that is known as a metadata. So when we have captured this imagery, what was the sun angle, what was the time, what was the cloud, like whether how much clouds were there in the imagery, how much cloud over ocean was there, how much cloud over land was there. So every details you will get as a metadata from the thing. Elevation is also there, ozone pressure. So this kind of data you will also get from this satellite, and that will be in the, it's a like metadata, which is the overall information about the data. Now I will just give you the information about one more satellite. Why? Because generally, like we do use this Landsat and Sentinel for most of the application in this remote sensing. So you should know more about it and you should be aware about it. So Sentinel 1, it gives the microwave remote sensing data, which can penetrate through cloud as well. So if cloud are there, then also it can give the data. But right now we'll not touch upon that. We'll go look into Sentinel 2, which is a multispectral data. There also you have two products, surface reflectance and top of the atmosphere. And here if you see, these images are available after 2017. Then if you see the bands here, then it has the bands of 10 meter, 20 meter, 60 meters. So that's what I was telling earlier also, that every band is not same. When we talk about Sentinel, we tell that it's just having 10 meter spatial resolution, but it's not true. It's not there for every band. Similarly for Landsat also, it's not true that it has all the bands as a 30 meter. Some bands which are there for temperature or some other thing, they might be at coarser resolutions as well. So here, if you see blue, green, red bands are at 10 meter resolution, and this near infrared band is also at 10 meter resolution. And these are the very high, like in this particular window, they are taking more number of data, which means the which resolution is more compared to Landsat. If we talk about if we compare these two satellite, Landsat and Sentinel. So in which terms let's first talk about the spatial resolution. Does Sentinel have high spatial resolution compared to Landsat? Any idea? So, do Sentinel has high spatial resolution compared to Landsat? Yes. So Landsat has 30 meter, whereas Sentinel has 10 meters. So high spatial resolution. If we consider the time, Landsat has revisit of 16 days, whereas the Sentinel has revisits of just 5 days. So temporal resolution is also high. If we know the spectral resolution, if you can see here properly, the number of bands which are available in sentinels are like high compared to the Landsat. So spectral resolution is also high, and this minimum maximum value, or you can say the radiometric resolution, it's not given here, but I think both of them have same spectral radiometric resolution, which is around 16 bit only. But that I think you can check from their description how much radiometric resolution do they have. So yeah, for more details on Sentinel-2 radiometric resolution, you can see this page. So let's just see if we are okay. This page is not working right now. So you can check more on that. But mostly the Sentinel-1 is good in terms of spatial resolution, temporal resolution, spectral resolutions, and radiometric resolution is more or less same. So I think after going through this much data set, I think you are more comfortable with the terminologies, which is spatial resolution, temporal resolution, spectral resolution, and radiometric resolution. And you can see a lot of images are being there stored in this Earth Engine data catalog. So you can check for different satellite, and you can check their specification, what is their spatial resolution, temporal resolution, radiometric resolution, and spectral resolution through this particular portal. Now let's get back to our PPT. Any doubt till now in this 4 resolution and how to check it for different imageries and what kind of common day data which we use in remote sensing applications? Any doubt till now? So basically, what I will refer is if you are working with remote sensing data, you should work with Google Earth Engine only. No need to use with any other software because it will give you more flexibility if you want to change your study area or if you want to change your timing or the temporal period through which you are doing. It has very much flexibility and you do not need much storage. You just need a normal laptop because everything is happening on browser, so you do not need much computational power as well. So I suggest you use Google Earth Engine only, and in that it has all the data sets available: Sentinel, Landsat, Modis, then ABHHR, some LULC products are also there. And further, if you are interested in more data, so there is a one community portal which is known as Awesome GE. So I will show you that particular website which you can note down. Uh, so in Google Earth Engine, some of the data sets are already available. But let's say if some data is not available, like which is generated by some of the people uh, during some research work or some in their organization. So that data is available in this particular website, which is Awesome GE Community Catalog. So here, if you click over here and then you go to data catalog, you are having lot of theme which are present over here. So here you have this fire related data, global events layer data, weather and climate data, biodiversity. So they've organized all the data depending on the application which we use. This is the elevation data set. So elevation, you have this many elevation data sets are there. The DM product which we discussed in the previous class. Then this is the soil data which it has. So it is 5 to 6 soil data as well. Then this LULC data set. So there also you 8 to 10 or more than 10 types of uh, LULC data is also available. And you can, if you just want to analyze any of the data sets, some data set are like future projections also that how urban areas will impact or something like that. So if you want to access any of these data sets, you just have to click on that particular, let's say I want to see this ESA world cover 10-meter map. Just click on that, and if you go down, it has sample code. So you do not have to write it by yourself, but sample code is already there. So you just click on that sample code, and once you open your Google Earth Engine, then you just click on run and you can adjust your code. So right now this data is for right world cover which is like land use land cover map. So it's taking time to load. So now you can see it just loaded all the data sets, and I can see over India what is the data. So let's say if we see over Gujarat Gandhinagar, so you can see this data sets now properly, and which are the different bands it is representing. So sentinel imager it is showing, then invalid image, or if you zoom in you will get more idea like what is there. So you can see different things, like different data sets are there on this particular portal. You can go and check out if it is relevant to you. You can use any of the data from here. So it is a lot of data. Yes. 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 Hmm. Okay, so which data you used, DM data you were trying to download? Is it SRTM or some other data sets? I can show you how to do that. So open topography, data catalog. So now if we go to SRTM 30-meter data, so which select region. Okay, and which like place you want to look for the data? Do you know the coordinate or tentative area? Yeah, see where it will be. Himachal, Srinagar. So can you locate somewhere here? Is it near Leh or Baramulla or something? I don't know. So do you know the Udhampur, Kishwar? It's near this one or okay, but I will show you like for this region only. It's available. So you can just click on select a region, and let's say this is area near Leh. So I have just selected the region, and I just downloaded this current selection area is approximately this much. So it has data, and then just download, and I think there is no issue. So if you know the coordinates, you can put here also. I think you might have clicked somewhere else. You might check that whether it's showing SRTM 30-meter only or not. But I think data is available for entire world. It's not like that it is not available. Uh, so here, wherever this red color is there, their data is available. This like whatever the area which are within this line of red color, data is available. If you don't get it, let's check. Which one? Okay, so I think this data set is I think available for US only. So this data set, if you talk, see wherever you take any data set, there might be written that for which region it is available. So see, this data set is available for this region only. The red part you see here, Can you see here this red portion? So this data set is available for this area only. And you can see the extent also for which it is available. And this is not the SRTM data. This is the some of the advanced data at very high resolution, which they've created using LiDAR, and that also for US region only, not for entire world. So here, I mean, if you need a product which will be there in India, this is 14 number shuttle radar topography mission SRTM global that is available for entire world. Then this allows world 3D 30 meter that is also available for entire world. Then this NASA DEM global digital elevation that is also available for entire world. Then this Copernicus global digital elevation model that is also available for entire world. After that, uh, these four are available for entire world. Apart from that, I think others are available for regional data most of the time. No, this portal is only for elevation data. That elevation data is not just them. It might be a drone data also, which is like in terms of point cloud. Okay, so basically any data which is captured using LiDAR, drone, or this kind of sensor which gives the DEM or DTM. So elevation data sets only related to the elevation data you can download from this site. But the good thing about this site is if you use other sites like such as USGS, Earth Explorer, and all. So at a time you can just download one tile only. And if you have a very big area, yes, 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 yes. So here the good thing is in this you have a lot of flexibility compared to USGS Earth Explorer. The limit which you can download is bigger one. So there, I think if you take 4 to 6 imagery, here you can download the same area in just one go. So the merge operation will not be that much which you need in USGS Earth Explorer. And if you will go to Google Earth Engine, then you can download any area in just one go. But for that, you need storage in your Google Drive, or else you need some storage or some time because it will take time. Google Earth Engine. These platforms are quite quick compared to that. But it's like always come with the like if you are using Earth Explorer, it will download it fast, but you need a storage to keep on to keep all the data and to process. So depending on like how you want to use it, you have to find the way. But mostly like I will refer this site only for elevation data downloads because it's very quick and compared to other sites, you can download more extent in just one go. Okay, so now I think we'll go to the satellite imagery part. So I think data part is quite clear now. So we will discuss more about the bands and composites. So if we have like imagery, then it has different bands as we discussed. So the band one is a coastal aerosol or the ultraviolet blue or something like that. So now you have then blue, green, red. Then this one is the near infrared. So you can see this image. The band number one is very dark in nature. Darker color means it is not reflecting anything. It's just like most of the things it is reflect like absorbing in that particular band, and we are not getting much information out of it. And because of that, we do not use band number one most of the time. Another thing is when we make a composite using these bands to visualize it in terms of colors. Generally, what data like satellite will capture it is in terms of black and white image only, whether you take any band, because just that particular band will show you that how much energy it sensed in that particular band from the object. So that will be between your radiometric resolution. If your radiometric resolution is a 4 bit, then that will be 2 to the power 4. So it will be 2 to the 0 to 15 bits. So now here in this case, if reflectance is more, it will show you the more white. If it is less, it will show black. So in RGB also, if you see, the reflectance is very less. But if you see towards the near infrared region, band number 5 and band number 6, then there is a much more reflectance, and you see the imageries are bright with gray and white colors. Now, when you have to create a composite to visualize the image, what you have to do is you have to take any three bands and you have to put into what we can visualize. So now if I human eyes can visualize three bands RGB. So from the given bands, if we take R and put R as a R, green as a green, and blue as a blue, then it is known as a true color composite. We can see the things as it is how we look for. It's like vegetation will look like as a green, snow will look like as a white color, water will look like as a blue color. So similar things which we can perceive through our eyes, we can perceive the same thing. But now, see, you can see these three bands RGB, they are having very less reflectance. But if we see this band number 5, which is near infrared, it has more reflectance. So if we want to utilize that particular stuff, then we have to use something else. So what do we do in that case is we will shift our band. Now what we will do is we will put green band in blue color, red band in green color, and this near infrared band into red color. So earlier what we did, green green, blue blue, red red, but now we shifted like this. So green we putting into blue, red into green, near infrared into red. So we shifted the band by one, and now whatever we will get, that will look something like this, which is known as a false color composite. Why false? Because it is not same as we see from our human eyes. Here vegetation is looking like as a red color, water is a dark color of shades of darker blue or darker black. And if you see that, can anyone tell me that why we are seeing more red color in the image? Yes, and the more thing, like this is the one thing. But now what we can see here, if you can compare these three band, green, red, and near infrared. In which band the values are high? Obviously near infrared, because you can see how you can see the image has more values, because if it is white, then it has more value. If it is black, it means there is nothing coming to the sensor, and because of that the color is black. So compared to this green and red, near infrared band is having. So you can see here, this compared to this green, red, and near infrared is having bright colors. And now, like if we when we take any color, it is a ratio of RGB color. We have 250 0 to 255 for blue, to 0 to 255 for green, 0 to 255 for red. So now you can see more values is coming where in near infrared band, which we are replacing as a red. And then what will happen compared to green and blue and green band, red values are more, and because of that it will show red color. Okay, so this is in terms of image, how the image manipulates or how the digital image processing works. Basically the data, and if we see the physical sense of it, then we have to see why there is a high reflectance in near infrared region. That is because of vegetation. Vegetation reflects a lot in near infrared region, and because of that values are very high in band number 5, which is near infrared, and values are high near infrared band, which we are representing as a red, and that's why red color is predominant. If we represent this near infrared band with green, then it will become more greenish. If we represent near infrared with blue, then it will become more bluish. So it depends, first thing is near infrared band is having high value compared to green and red, And the second thing is that near infrared band, we are showing it as a red. That's why the image in false color composite looks as a red. Any doubt in this concept? Hmm. Yes, yes. So what you should respond it as a generally in true color composite, we put green as a green band, sorry, blue as a blue, green as a green, and red as a red band. However, in false color composite, we replace green in blue, red in green, and near infrared into red channel. And now in near infrared have high reflectance compared to green and red, which we are representing as a red color, and that's why our uh, false color in composite shows more reddish values. And primarily this is driven by the vegetation. So you have to say you have to, when you answer something, you have to use both the things. The first thing is why there is high reflectance in near infrared band. So that is because of vegetation. And the second thing is that near infrared band you are putting into red band. That's why. So these are the both the region. You have to include these two region together. Got it? So the good question. So here you can see, I mean the earlier image if we take and this image we take, let's say do that thing and check it out. So we have this image which is true color composite and this is false color composite. So this is from the same area. Now if I ask you if you have to differentiate between vegetation and water, in which image it is easy? So my question is you have to identify water bodies. Yes. So basically, it increases the contrast between different features. The abscissa image increases contrast, and because of that, it makes the identification easy. Now, in the abscissa, if we want to identify water, then it's very easy compared to this false color, true color composite. Here, in true color composite, in some of the locations, we are not able to see proper water as well. So, if you see this area, like here, water is not clearly visible. It's like merging with the landscape. It's kind of greenish blue color. So because of that, it is very difficult. Here also, if you see, this looks black, but this is not because of water. This is because of shadow. Here, this water body, it is also not detectable properly. But if you see here, it is like contrast is too much and you can identify the things very easily. And that is the solely reason to use the false color composite. Only reason is that it will create the contrast. Because of that, it is easy to differentiate between two objects. Got my point? Yes. So why? Because like if you take snow, it's white, and because of that, it has very high reflectance compared to other objects. So when we talk about these RGB bands, then also it will have very high values. When we take near infrared also, there also it will have very high values. And because of that, you will see every time it is a white. So compared to other objects, snow is already white only. So it will not absorb anything. It will, whatever is just coming, it will just reflect in all the bands. And because of that only, we are having snow as a most of the time white only in image also, whether it's a HCC or whether it's a true color composite. Okay. Okay, so I think if this concept is three. So basically, there is another thing which is known as a spectral signature. So this the contrast and what we discussed till now. So that concept which we will be used in our remote sensing, and like as human, how we identify the other human based on their characteristic. Same thing we do in this remote sensing. If I want to identify water or snow or grass, we have spectral signature that will guide you that this is water, this is grass. So if you take this green line, so you can see around this zero point 0.4 to zero point 0.7 is your visible spectrum. So RGB band will come into this one. Now this one is a near infrared vision after zero point 0.8. So here you can see the vegetation is having high reflectance. But if you see the clouds or snow, it is having very high reflectance in all the channels, R, G, B, near infrared, everywhere. And because of that, it looks same, white in both. But here, if you see this vegetation, it has very less reflectance in RGB band, but high reflectance in near infrared band. Because of that, this band we are showing it as a red. It is looks like. Got? Okay, so before like starting any remote sensing application where you want to identify something, you have to plot the spectral signature curve, that how my object is behaving under different bands. And using that, you can choose the band. Like on this image, you can put your your bands, and then you can identify that which bands should I use in my analysis. So that is the first step when we start with any remote sensing data, which we do is the spectral signature and identifying which band should I use to detect something. So this is like how we can detect the different leaves or vegetation. If it is more green, it means it has lots of chlorophyll into it, and it will reflect a more of near infrared lights. And this happens because of that structure that you will learn in detail during the class time. Based on that, we derive some indices which will create a lot of contrast, which is known as a normalized difference to vegetation index, where we take a ratio of normalized ratio of two bands, which is one band in which we are having high reflectance and one band in which we are having very low reflectance. So the difference between these two will create high contrast, which will help us to differentiate a lot of things. So here I have just taken as an example. So area near IIT Gandhinagar, I have divided into two parts, water and vegetation. I have extracted the data of all the bands for water and vegetation, and what this is the reflectance value which I am getting for all the points. And then after, if you will plot here, then you see this band 4 is red band. So in red band, both water and vegetation have similar reflectance. But if you see this near infrared band, band number 8, then you see a lot of difference that water does not reflect anything. It absorbs everything in near infrared region. Whereas this vegetation reflects around 35 to 40% into near infrared region. And because of that, if we take the ratio as near infrared minus red divided by near infrared plus red, then we will end up with this index which we can identify water. So if it is less than 0, then it means we are having water. If it is greater than 0, it means we are having vegetation. And higher it is near to the 1. Higher it is near to the 1, it means what? It will have more number of more NIR content or more green color, and because of that it will reflect more in near infrared and less in red. So it will become 0 and it will become 1. So you will get image like this. So if it is more negative, then it will show it as a water, and wherever it is a green patches or patches of vegetation, it will show as a green. So like that we do the classification, and all the pixel values which are coming in between, that is known as your noise, which will shown by the buildings and all. So this is the applications, like how the if you plot the animation, how it will look like, and it will help you to do the different things. So this is the another applications of how the forest loss is happening in the Brazil. So you can plot the NDVI value, and you can for different years, and you can check out how it is happening. This is one more other applications of forest fire. Um, so how much forest loss has happened between 2 years, between 2001 to 2015. So you can check out here. So these are the applications which we can do. And this is for fire application. I think we'll not go much detail into fire. Okay, just we'll do one thing because we do not have much more time in this class left now. So I think I will just take one example. So I think you have heard about winds displacement law in these classes. Yes or no? Yes. Have you heard of it? Yes. So what does it? This law states is that the at if object has temperature T, then how much maximum radiation it can emit. So that is defined by the lambda max is equal to 2898 divided by T. So if we take if any forest fire is happening and that has, let's say, 200 or 300 Kelvin temperature, or let's say 500 to 1000 Kelvin temperature. So now if you put 500 or 1000 here, this lambda max will become 3 to 5 micrometer. So when you start identifying which satellite I will use to monitor forest fire, then you have to use the satellite which ranges between this to this band, 3 micrometer to 5 micrometer. So this winds displacement law help us to identify the wavelength which is necessary, to which we have to make our sensor, so that it can helpful to us to measure the fire and other things. So we'll design our sensors accordingly by studying the different events which happen over here. So this is the Modi's satellite, and in that these are the different bands wavelength which it has. So we can select the bands which are between 3 micrometer to 5 micrometer. So this bands 20, 21, so between 3 to 5. So this we can use for mapping forest fire. So you can see here the band number 21, band number 22, that is useful for fire detection and characterization. Okay, so this is like how we use winds displacement law for forest fire. And then this is like how we detect forest fire at a remote sensing image. I think if you are interested, then we can discuss this in detail into the next class. Otherwise, we will not able to finish our question answers. So this is about forest fire, and then once we have all the data with you, then you can use some GIS tools such as QGIS or something else after collecting all the satellite data, and then you can use them, plug all the layer into one application, and you can create a lot of decision-making tools from out of it. So now let's see some of the questions which I have in this. So let's start with which model has the building height information, DSM. Okay, right. Then choose the correct statement. Okay, so DTM may be interpolated to generate DM. That is true. But the second statement, DEM and DTM both are same or not? Is it true or false? What about the option number B? Is it true or false? So what is the differentiate between DEM and DTM? So if you have heard, then DEM is just raster data in which we have continuous data. But DTM is just in which we have linear feature. If you have recall it properly, that DTM is more kind of like we have in DTM more kind of line network. If the slopes are there, then it is represented by line. And then we interpolate those line feature or linear features, and then we will get the DA. So that's why both are not same. Then TEEN is a triangular irregular network. It's not a raster data. It's another type of data. So that's why option C is also wrong. But DM is a raster data. So that statement is true because it's just continuous in nature. Okay. So now the next question is digital photogrammetry is also called as uh, no, see, terrestrial means what? Which we do on terrestrial. Terrestrial means like on surface of the earth. But this we do not do on the surface. This we do from the satellites. So what will happen in that case? What data will we get it in terms of electronic format, or we can say it as a soft copy. It means like data is not as a map, it's as a electronic form, or rather than using the electronic form because we are not dealing with 0 1 binaries and values, it's kind of soft copy. Okay, so it's not a terrestrial because terrestrial we have to fix instruments and then we do that is terrestrial. AR VR is also not that, electronic is also true. So these are the mostly based on the lecture slides, so which I kept. Uh, the input data for digital photogrammetry are okay. So the answer is lidar plus scanned aerial photographs, both. So in lidar also we try to collect data and through which we will develop this DEM and all because of that. Uh, then we have this remote sensing techniques. We use the property of no. No, see, here we use electromagnetic spectrum. So the answer is electromagnetic spectrum is a 92 waves are there at 90-degree angle. So the answer is electromagnetic waves, not the sound wave and electric wave. It's a combination of both electromagnetic waves. If you have heard, see this kind of things are there. 90-degree, two waves. Yes. No, it's not a separate sound wave or something like that. It's just electromagnetic spectrum, which is a combination of both. Like if you see the signal, it's coming in this direction also and this direction also. So it's a electromagnetic wave. So which is not an element of remote sensing. Yes, true. So the visible wavelength, yes. So we have from point 4 to point 7, we have electromagnetic. So this is the what I'm talking about. This electromagnetic spectrum where we have point 4 to point 7 as a visible, then infrared as a point from point 7 to 100, reflected infrared. Uh, so out of AC in infrared also you have two things. One is reflected and one is thermal. So what is the physics behind those two? Why, how they are different? Like this reflected are between 0.7 to 3 only, but this thermal is from 3 to 100. So what is the difference between these two? Yes. And what about thermal? Yes. So object have some temperature and through which it will emit the radiations and that we are measuring in remote sensing that will be captured in thermal remote sensing. And microwave it means the active remote sensing where we will send signals and then we will capture those signals. So which is at a very high wavelength. And micro radio wave will be more high spatial wavelength, which will be used for communication purpose as well. Now, which of the following wave is employed, not employed in remote sensing? So now I think when these rays come into atmosphere, it will interact with the particles present in the atmosphere, and based on that, there will lots of interactions will happen. That is known as the scattering. And there are three types of scattering: relay, me, and non-selective scattering, depending on the molecule through which it is interacting. If the molecule is same as the wavelength of the light which is coming from sun, then it will create a me scattering. If it is a lesser than that, it will create a relay scattering. And if it will just very big, then it will scatter here and there, and it will cause the non-selective scattering. So based on this scattering principle, uh, tell me that which one of the following statement or are incorrect. Okay. Any other? So let's see. So option B, C, and D all are incorrect. And why? See, the first one is longer wavelength scatters more than the shorter one. So that is not true. Depending on the like shorter will scatter more. Why? Because it is similar to the size of these molecules, whereas longer will bypass the different signal like this molecules, and because of that, it will not scatter more. And if you see this scattering, then it has the proportion like of 1 to the power lambda 4. So it's like higher the sorry, lesser the wavelength, more is the scattering. Higher the wavelength, lesser is the scattering. So scattering is proportional to this term. Now, when we talk about the another one, see, the scattering is easy to predict. So there is so many randomness is there in this mechanism. We don't know the molecules which are present in the atmosphere. We do not know the waves which are coming, and because of that, it becomes very uneasy to predict those things. And that's why it's not easy to predict scattering. Then the third one is Rayleigh scattering takes place in the upper 6.5 kilometer of the atmosphere. So here you see it is mostly gas molecules which is present in the lower atmosphere rather than in the upper atmosphere, and because of that it will not happen there. So that's why these options are incorrect. Then we have next question, which is the yes D. Yes. So if you see the relay scattering happens because of these gas molecules. And if you see this small molecules which are there, it is like in the troposphere only, and which will be like around 4.5 kilometer only, the lower atmosphere. Like if you see that after 6.5 to 7, all this like half of the atmosphere will become empty, and most of the molecules which are present here, this gas molecules, they are in the lower atmosphere, and because of that, this scattering will happen in the lower part rather than in the happening in the upper part. Lower atmosphere. Yes, like if you go beyond 6.5, there is very less gases are present. very less gases in not just small or big, but in general, very less molecules are present after, like most of them are present within the 4.5 kilometer only. Okay. No, gases are present in the lower portion, like all the gases which are there, like if you take the oxygen, nitrogen. So all the gases, most of them, like any gas if you take, and most of the atmosphere, it's present within the 4.5 kilometer only. So all this scattering which will happen, it will happen mostly in the troposphere. Okay. Still, if you go through it, if you have still any confusion into it, I will come up with more illustrations on that with atmospheric density and all in the next class. If you just drop a mail to me or write in discussion session, we will discuss it more there. Okay. So next we have which of the particle size found the non-selective scattering. So this is kind of textbook. Yes, it's more, the size is very more, so it's 10 more than 10 micrometer, where particles are very bigger one. Now these are some questions from the previous year GATE question papers of geomatics engineering. Uh, so this is the electromagnetic spectrums can be broadly divided as and in order of increasing wavelength. Which of the following is true? So gamma ray, X-ray, ultraviolet, visible, infrared, microwave, radio. Next question is the relationship between the wavelength, frequency, and velocity uh, is. Okay. B nahi, it's a C. V lambda. C is equal to F lambda. We say like the speed of light is equal to F lambda. So it's a frequency into wavelength. The next one is the active remote sensing. Remote Earth objects from the satellite bone sensor. The source of the energy used for sensing lies at. So can you tell me first the difference between active and passive remote sensing? So the question is asking where do we put that source of energy? So obviously, like we put that on satellite, so that satellite when satellite is capturing, like we do with our mobile phones, we keep our flashlight on, so it will create artificial lights, and then we'll take the photo. The next one is which of the following statement is correct? So in optical remote sensing, more often we are interested in diffuse reflections. The reflection will be diffused if the incident wavelength is comparatively much larger than the surface roughness. So diffusion means scattering, which is happening at the surface. So you can just keep this thing in mind, specular and diffuse. So first of all, what principle we use in remote sensing? Is it specular one or the diffuse one? Yes. So in optical remote sensing, more often we are interested in diffuse reflection. So that is wrong. The second thing is the reflection will be diffuse if the incident wavelength is comparatively much larger than the surface roughness. So here it's the same thing which you learned in the scattering that will come into picture, that when it will happen like this, what is telling is the reflection will be diffuse if the incident wavelength is comparatively much larger than the roughness. So if it is much larger, then it will happen or not. So that, okay. So the option number, okay, sorry. So the first one is correct. Why? Because see, if this thing will happen, like if this reflection will happen directly, then we might lose something. So it's reflections only, but it's a bit diffuse reflections. Why diffuse reflections? It's because, see, if it will happen directly like specular reflection, then what will happen? Then satellite is here. Let's say satellite is here, and if everything will go into just one direction, then satellite will not be able to capture it like every time. So let's say if this is the geometry which it is following, the object, then what will happen, that satellite will not capture this thing every time. It will just, but in terms of little bit diffuse reflection, what will happen, that some rays are coming from here also, like this is the natural terrain, how it will look like. And then energy is being reflected only, but diffuse reflection. It means it is not coming just from one angle, it's coming from different angle. That's what we talked when we talked about this top of the atmospheric reflectance and surface reflectance. And then this one, second one is wrong only. Then the surface that reflects microwave in specular manner, basically, if the size of the wavelength and size of the this roughness which is same, then it will become a specular one. Otherwise, if the roughness is more compared to the wavelength which is coming, then it will become more scattered. So surface that reflects microwave in specular manner may reflect the visible in the diffuse manner. So what will happen in microwave? So microwave it is in specular. It means whatever is coming, it is going with the same angle. It means if that is happening in the microwave, then if we reduce the wavelength of it, then what will happen? This roughness is more compared to the wavelength which is coming, and because of that, the visible lights will become diffused. So at a given surface, you are having this kind of wavelength, and this surface roughness is also the same wavelength. Then it will reflect, specular reflection will happen. But now if you will reduce this wavelength like this, compared to this surface roughness, now surface roughness is more, and because of that, it will get diffuse and it will go here and there. So basically we are reducing the wavelength, and because of that it is becoming diffused. So that's why option C is right. Then all the wavelength emitted by sun reflects in diffuse manner from the object on the surface of the earth. So that is not true, because it will depend on the roughness of the surface, how, what is the roughness, and depending on that it will become a specular or the diffuse one. So that's why this one is wrong. And the reflection will be diffuse if the incident wavelength is comparatively much larger than the surface roughness. So if it is more compared to the surface roughness, it will just become specular, not the diffused one. So that's why that is wrong. Okay, we'll now move to the next question. So part of the solar radiation incident on the water surface gets refracted as per which law? So when we talk about water, it is a surface. So the energy is interacting with surface. So there is a Snell's law which says as n1 sine theta 1 is equal to n2 sine theta 2. So which is for like reflection and diffractions. So it will be Snell's law. Then which of the following parts of electromagnetic spectrum is or are used in satellite remote sensing for Earth observations? So which one is true here? So the true answer is we use all the three: visible, thermal infrared, and radio waves. Gamma waves we do not use. The next question is spectral signature of an object in a satellite image does not depend on the spectral signature we discussed, how it behaves in the different wavelength. So that spectral signature does not depend on, so see, season of the year. So if we have dry season or we have spring season, then it will have different greenness value and different chlorophyll content, and because of that it will affect. But if we have this wavelength of electromagnetic spectrum, so that is also thing that if the wavelength is less or high, it will have an issue. Then we have SWAT width of the satellite. So it does not matter that what is a how much area it is covering. If it is covering small area also, if it is covering large area also, the spectral signature will remain same only. And then reflectance value from the object. So that is a true part which we have to consider. So option uh, A, B, and D are correct, and C is wrong. Any doubt? If any point of time, if you think there is a doubt, just please stop me, unmute yourself, and stop me. The next question is thermal infrared images are provided by. So this is just you should know more about the data sets. So we know that Landsat provides this thermal infrared image, and this Landsat TM, which is a thematic mapper, it provides. Whereas this Quick Bird is just high resolution imagery, and Econos is also. So they don't provide. Cartosat and Sport is also for high resolution, and this is for India at 32-meter resolution. So this do not provide any thermal imagery. So this like TM and this NOAA AVHR, both sensors are provided, whereas India's LEAS 3 also does not provide thermal image. So this answer is this one. MSS is till Landsat 5, they do not have thermal band, and then they incorporated afterward TM band. Now, I think you can try to give answer of this question. So, in comparison of this true color composite and false color composite, which of the following statement is correct? Correctly, both are correct. Okay, fine. And now this one, choose the correct statement in case of visual image interpretation. So, first thing which we start. Hmm. So, first is right, C is right. The other two are wrong. Okay. The visually distinguish between river channel and canal on an image having a similar width and located in the same area. The most important parameter used is shape, because canal will have defined shape whereas river have this kind of meanders and it will not give proper. Now in terms of hyperspectral image, which statement is correct? So hyper means more number of, and spectral means spectral resolution, where we talk about number of bands. So if we just decode that particular word only, I yes, exactly. So that is a true. number of bands are more, and then bandwidth is also narrow, and bands are continuous. Hyper, like we have multiple bands, so all the bands has like just placed simultaneously near to each other. So width is also low, and they are continuous in nature. So I'm here the T. Okay, I think we will stop here. We have a few more questions in this. Uh, we are leaving with few more questions are there. So we'll I think take it in the next class. Before that, how was today's lecture? Any comment on this? So any suggestion for the upcoming lecture? I think we have discussed sufficient data and all. And questions, I think we are short of not discuss question much. So in the next class, we will start with question answer rather than going to the concept. But this is concept delivering was necessary before jumping to this part. So are you guys clear with your remote sensing concepts, or is there any doubt in the concepts? Okay, so I think yes, yes. So you can drop me an email. I will list some of the link there. You can connect with me on LinkedIn or Instagram, or just write a mail to me, or you can just put the thing in this discussion session also in NPTEL course discussion forum. I will share some of the courses there. Whatever is fine for you, I will share the details there. So I will share my email ID. But always you can contact with this NPTEL discussion forum. Other tutors are also there. If you have any doubts or suggestions for learning, they will suggest you the sources. Okay, if there is no further question, we'll solve some more question answer in the next class, and then see some of the applications how we can use remote sensing using this Google Earth engine for practical applications, basically floods or flash floods, something like that. Okay, so if not any question, then we think we will conclude this session for today. And happy Janmashtami to all of you. Uh, have a nice day. Bye bye. Bye bye.